First of all, I would like to say welcome to the International Space Science Institute Game Changers online seminar. I would like to say already hi to all the 100 and more than 10 participants which already wrote on the chat and say hi to us. I would like to welcome them all of you. EC is celebrating 25 years this year. And the EC is an international institute where people can meet to do science in Bern. And this year, because of the COVID-19, I would call it disaster, people cannot anymore meet so easily in Bern to do science, to have informal meetings and to exchange their view, to analyze data and to do theory and simulations. So EC could actually not anymore serve the space science community as we are used to do since 25 years of success, I have to say. So EC, to serve anyway the space science community, came up with this Game Changers online seminar. Until now we had 12 seminars dealing on how mission changed our view of the solar system. Now we will have a series of 7 online Game Changer seminar on how mission changed our view of the universe. And I'm particularly happy today to have Enrico Bozzo speaking on Integral, the Extreme Universe. Enrico Bozzo graduated at the University of Rome, and then he moved in 2009 to the Integral Science Data Center in Versoix, the Department of Astronomy of the University of Geneva. He's very well known in data analysis, not only on integral, but he's also known on doing theoretical and analytical theoretical works. In 2009, when he joined Integral, he's coordinating part of the science ground segment operations, involving in the overviewing of the data processing and distribution to the community, as well as the quick looking. Enrico Bozzo, I have to say, it's a brilliant young scientist, but not only scientist, he's also becoming more a manager and involved in several future space missions like Euclid, Theseus, EXTP, and Athena. So I'm particularly happy, Enrico, to have you here today and to speak about Integral as a game changer mission. So the screen is yours. I cannot say the floor, but the screen is yours.
Okay, thank you very much, Maurizio, for this nice and kind introduction. I hope you can all hear me well. So let me first thank not only Maurizio, of course, but all the organizers of these interesting meetings. It's really a pleasure today to speak a bit about Integral, the International Gamma Ray Astrophysics Laboratory that you can see sketched here on the first slide. Now, the Integral motto is usually seeking out the extremes of the universe, and in the next slides we will see why is that. So first of all, Integral is an ESA-led mission. ESA stands for European Space Agency. So you can see in this slide the whole ESA fleet as of today, and you can see that Integral is the rightmost mission, meaning that it's exploring the hardest energy part of the universe. It has some overlap with XMM Newton that stops at softer X-rays, while Integral is observing more in the hard X-ray to the gamma ray domain. Indeed, Integral was designed to explore what we call the non-thermal universe. This means the universe characterized by violent events like supernova explosion, relativistic acceleration, accretion, ejection phenomena, and whatever basically happens in environments at around 10 million degrees and above. So in the energy domain between KV and MeV as sketched in this plot. So just to start with some history, you can see here photos dating back before the launch. that occurred in 2002, 17 of October. It was used a Proton Russian launcher. You can see also the photo of the launcher here. And the satellite, it was quite big, 5 meters high and over 4 tons in weight. So it's really a big machine. As you will see, it hosts several instruments. And it was launched in a quite elongated orbit that you see also sketched in this slide. It takes about nowadays 2.7 days to go all along this orbit, and it achieved at the furthest point from the Earth a distance of about 153,000 kilometers. Now, this orbit is actually a key property of Integral because it allowed the satellite to perform a long observation in a certain direction in the sky that, as we will see, is quite important to achieve all the results that I will mention later. So let me discuss a bit about the instruments on board the Integral. So we have in total 4 instruments that you see listed on the left. The first one is IBIS. It's called the hard X-ray gamma ray imager on board the Integral. This is because it's an instrument endowed with a very large field of view, and it covers also a wide energy domain from 15 keV to 10 MeV, and it's able to image large portions of the sky at once, 30 by 30 degrees, with an angular resolution of 12 arc minutes. Now, for people coming from other domains like optical astronomy and so on, 12 arc minutes could sound like a lousy resolution, but of course here we are dealing with images in the hard X-ray that are quite complex to achieve, and as you will see, indeed, this is a very good angular resolution. It allowed the instrument to achieve unprecedented results. The second instrument is SPI. This one can also perform images of the sky, although with some lower resolution, down to 2.5 degree in angular resolution, but it has a very good energy resolution. So basically, it is designed to perform a wide energy range spectroscopy from more or less 20 keV to 8 MeV. The energy resolution is very good. You can see 3 keV at 1.7 MeV with some dependence of the energy, but it gives you the order, an estimate of the order of magnitude. Then we have 2 identical instruments that are called GEMIX-1 and GEMIX-2. These are 2 X-ray monitors. They cover the sky between 3 and 35 keV. So you see a lower energy range compared to the others, but still some significant overlap. And the 2 GEMIX are also providing images of the sky in this energy range with a very good angular resolution down to 3 arc minutes, although on a smaller field of view compared to IBIS. The field of view is about 4.5 degrees in radius, so it's a circular field of view. And it completes the payload, a small optical monitor working in the visual band, a 5 centimeter aperture. And what is important to note is that all these instruments are operating simultaneously. So at any time, Integral is providing a huge and rich amount of data sets for each observation. Now, just some, out of curiosity, some picture of the instruments, again, dating back before the launch. You can see on the top left, the optical monitor. Below, you see SPI with the germanium detectors. On the right, top right, you see one of the 2 identical GEMIX, and below you see the IBIS instrument that actually has 2 different focal plane. One is located above and is the ISGRI detector operating somewhat lower energies, and then you have the PIXIT detector that is located at the bottom and is collecting photons that are also passing through ISGRI. Now, what is important to note in these photos is that each of the 3 high energy instruments, so SPI, GEMIX, and IBIS, they are equipped with a coded mask on top of them. The coded mask is the technique that is used by these instruments to image the hard X-ray and the gamma ray sky. So let me just introduce a bit what is a coded mask, because of course this is a key observational property of integral. So the problem here is that if you want to image the sky in the hard X-ray and gamma ray domain, you cannot use anymore the technique that, for example, is being exploited by XMM at softer X-ray, that is the high grating incident gold covered mirrors, because I mean the high incidence, grating incidents only work for soft X-rays. It stops more or less at 10 keV. It means that higher energy photons are just passing through the mirror. So you need another technique. This technique is the coded mask. So the coded mask is basically a device comprising both transparent and opaque materials arranged in a certain pattern, as you can see on the right in this image. And what happens is that when you have a source in the sky shining through the mask, this one produces a shadogram, what we call a shadogram, on your detector that is located below the mask. And of course, if you have more than one source, then you have an overlap, a combination of this shadogram. So with the coded mask technique, you don't need to really focus the hard X-ray photons. You collect with this technique, but of course, the outcome is not a direct imaging of the sky, is a reconstruction of the sky image, because you need some software algorithm to starting from the overlapped shadowgrams to reconstruct the positions of the sources in the sky. So on the left, you see the outcome, just one example. This is an IBIS image, and this is not, as I said, a direct image of the sky. So you can consider that this image is actually a map of probability. So the brighter the source you see here, it tells you that the higher is the probability that we are confident that the source is there. So that's what imaging the sky with coded mask means. Now, let's say, apart from this complex technique, there is an advantage of recording X and gamma ray photons. That is, for each photons, you are not only recording with your detector the position on the sky, but you also record the energy and the arrival time. So it means that with your instruments, basically, you can perform images resolved in energy, but also resolved in time. Or say in different words, basically, you can, with all the photons you collect, study the distribution of the photons as a function of energy, meaning you are doing spectroscopic analysis, or you are recording the distribution of photons as a function of time. So you are doing a time analysis to study variability or detect periodic, aperiodic variability, and so on. Another drawback, say, of studying the universe in this energy range is that we are really photon starved, meaning that if we make a comparison with the optical domain, if you observe the Sirius star, for example, you get something around 360,000 optical photons per hour per centimeter square on your detector. In gamma ray, if you observe the crab, that is the brightest persistent object in the sky at hard X-ray and gamma rays, well, you get 3 gamma ray photons per hour per centimeter square. So this tells you and explains why with integral, in particular, we need long exposures in a certain direction of the sky in order to get the optimal signal to noise ratio. Now, there is an important point that actually became more and more important in the latest years, that are the presence of, let's say, 2 additional instruments on board coming for free. So these are the SPI anti-coincidence system and the IBIS veto. Without going into many details, what I want to mention is that these are active shields that were designed originally to screen the IBIS and the SPI instruments from high energy particles, for example, passing through the spacecraft and depositing energy in the camera. So they are used to filter out these events in order to recognize properly the real photons passing through the mask. But of course, it means that having these active shields, you are also having 2 very powerful instruments that are looking everywhere in the sky, because they monitor, let's say, the hard X-ray and the gamma ray background. They cannot measure the position of the photons because they are collecting events from all around the sky. But of course, if you have a spike event in gamma rays or Arctic rays, they can see the spike event as a kind of fluctuations over the background. So they are not only used to optimize the sensitivity of IBIS and SPI, but they can also be used as instruments by themselves. And as you will see, they actually came out to be very powerful. So in the plot here, you can see the field of view in green, for example, of the SPI ATS compared to the position of the spacecraft, and the extension of the shaded region is basically a measurement of the sensitivity. So the larger region gives you a higher sensitivity. Of course, there are regions where the sensitivity is limited because the visibility of the ATS is also limited sometimes by structures on the spacecraft. But you can see that this one particularly is looking everywhere around the spacecraft. So it has what we call an omnidirectional visibility of the sky. Now, the last peculiar and important property of Integral is that the spacecraft was designed to continuously transmit the data stream along the orbit. It means that the delay between the observation and the actual availability of the data is only a few hours. And it is why we can say that Integral allow us or grant us access to near real-time observations of the sky in Arctic ray and gamma ray. And indeed, for example, in Versoix, this research center where we receive the telemetry and process the telemetry in order to visualize the data, we have scientists on duty that are looking at the sky all the time. And in case any interesting event is occurring, of course, they can alert the worldwide community about this event and eventually plan other observations. So the institute we are working in, let me say, in which I'm also sitting right now, is sketching this slide. This is a photo you can see is a nice old building, and looking for us from outside, you will never say that people inside are looking at the gamma ray sky, but indeed that's what's actually happening. So how do we exploit scientifically all this powerful suite of instruments? Well, what I'm trying to report in the next slides is a collection of the integral results that, of course, changed our view of the high energy sky. So let me start by mentioning the first key capability, that is the capability of performing gamma ray line spectroscopy and imaging of the sky. As of today, Integral is the only instrument that is able to do that. So in this first result, you can see here that Integral was able to detect the first ever evidence of radioactive decay of cobalt-56 into iron-56 in a type 1 supernova. This one in particular is supernova 2014J that went off in M82, 3.5 megaparsec away from us. Now, during the explosion, you indeed expect this kind of decay, but it was never observed so far. During this decay, as it is sketched on the left, you see we expect the release of gamma ray photons, one in particular between around 847 keV, and on the bottom you can see the SPI image of the sky in a narrow energy range around the expected energy of the photons, and you can see that there is a bright peak in the middle. This is indeed, if you look on the right, this emission line in the spectrum that you expected theoretically, and Integral was the first and so far the only one to be able to catch this decay. Of course, studying the decay gives you access to the physics of the explosion, so it's particularly important also to measure the way in which supernovae are, let's say, polluting our environment with heavy elements. So still keeping on the field of gamma ray lines, another very important result is reported here. This is another gamma ray line, this time at 1.809 MeV, so even harder energies than before. and this is a line expected during the decay of the unstable aluminum 26 isotope, as you can see sketched on the left. Here we have the release of a gamma ray photons, indeed at 1.8 MeV, and this kind of decay is expected to occur in massive stars as well as supernovae, and the decay time of this element is about 10 to 6 years. That is indeed the lifetime, the expected lifetime for massive stars. And as we know, supernovae and massive stars, with their explosions and their strong wind, they produce around them super bubbles that are indeed filled also with this element, and where you expect to find this line. Indeed, you can see on the right the map of the sky built at this energy with P. You see these super bubbles in the Milky Way, so in the center of our galaxy and the plan of our galaxy. And what is very interesting is that the unique capabilities of SPI do not only allow us to detect clearly the line, but also to measure the Doppler effect due to the rotation of the galaxy. So on the bottom, you can see that these authors were able to find indeed the motion of the super bubbles following the rotation of the galaxy with a velocity that is around 250 kilometers per second. Again, let me stress that Integral is so far the only instrument that can perform this kind of measurements. So let's change now key capability. We go to gamma ray polarimetry. Again, this is a unique observational capability of Integral. In particular, IBIS can be used to perform also polarimetry measurements in the gamma ray domain. To do that, what you're doing basically is to take advantage of the scatter of the photons between the ISGRI and the PIXIT detectors inside the IBIS. And you need, of course, a lot of photons to do that. So you need a very bright X-ray source. In this case, what was used is Sirius X1. This one, a very well-known black hole binary in our galaxy. So a source comprising a black hole and a massive star, as you can see in the animation on the right. And what Integral was able to find basically is that when you study the spectroscopic distribution of the photons, you see that there is a hard component extending from 400 keV and above, where indeed it was possible to measure a high degree of polarization. And it is believed that this component comes from the jet, because high polarization means somehow an ordered magnetic field. So this is where you expect to find the ordered magnetic field in this region. And of course, there are plenty of papers exploiting these results together with polarization in other wavelengths. But again, Integral is the only one that can measure polarization in this energy domain. Now, going to the ability of monitoring the sky all the time in every direction, of course, this is a very important capability to observe bright impulsive events, as I was saying before. The most famous one are the gamma ray bursts. These are, for those of you who are not familiar with GRBs, gamma ray bursts are very bright flashes of gamma ray occurring homogeneously in the sky up to cosmological distances. What we know so far is that basically there is a kind of central engine that could be the merging of two neutron stars or the explosion of a very massive star called hypernova. During this event, you create a lot of ejecta with shocks and so on at high velocity. So you release the gamma rays, and then when the ejecta slow down, you are also able to observe these events at lower energies down to radio waves. But you can see on the left that for just a fraction of a second or a few seconds at the most, each of these gamma ray flash is becoming basically the brightest source in gamma ray in the sky. The problem is that the position is random and it lasts very shortly, so you need omnidirectional viewing or anyway large field of view to detect these events. Indeed, since the early conception of the mission, Integral implemented also for EBIS a way to detect these events that is called IBUS, the Integral Burst Alert System. This is a software running on the ground that perform a quick analysis of the data even before they are completely processed to produce the near real-time version. So it's a very, very quick system. And in case any of these events is found, as you can see, IBIS is also is exploiting IBUS is exploiting IBIS data, so it performs also images of the sky, can localize these events. So when one of these events is found, the system call us on the phone by SMS. You have to wake up because usually gamma ray bursts like to take off during nights, whatever part of the world you are. And then you can alert the community in order to program other observations. Of course, robotic telescopes are informed immediately, automatically by the IBUS system and can already point in that direction. Now, we have here a sample of light curve, but this is just to show you the very good time resolution. So these are events that last a few seconds, but you can go down to the milliseconds variability study. You see if the event is bright, you have very nice light curve. And of course, also the SPACS, the omnidirectional monitor, can detect these events. You can study the light curve. You cannot localize them, but still you can perform studies of the shape and structures of the light curve that so much can tell you about the physics of gamma ray bursts. Now, speaking about impulsive event, of course, everyone knows about the detection of the first gravitational wave in 2015 that led to the Nobel Prize. I'm not spending here a lot of time because otherwise the talk will only be about gravitational waves. But just let me say that, of course, when one of these events occurs, you also try to look for electromagnetic counterparts. And clearly, Integral is a perfect instrument to do that, given this large field of view and omnidirectional visibility. Now, for the event of 2015, that was the merging of two black holes, we did not detect any counterpart, but you can see on the map on the left that the SPACS, this omnidirectional monitor, could look at any direction in the sky, and in particular, it was able to fully cover the region depicted in black, that is the LIGO localization region. Now, our light curve on the bottom left did not see any excess, so any electromagnetic counterpart. There is some different results from Fermi. This is a long debate, so I'm not going to enter many details, but it is just to show the powerful of Integral because we can follow the whole sky easily in order to search for electromagnetic counterparts. Now, of course, we were much more lucky for the 2017 event that was the merging of two neutron stars. So you can see on the left the plot by LIGO with the detection of the gravitational wave. But then you can also see that both Integral and Fermi were able to find an electromagnetic counterpart in Integral by the SPACS, this spike in gamma ray that indeed was a hard X-ray gamma ray counterpart of the merger of two neutron stars. And of course, this is a very important result that gave Integral a new life because now the mission is being somehow replanned to also follow up as quickly as possible these events. So on one side, we know that gravitational wave observatories, they will be improved over the future in order to detect many more of these events. And what we have done in collaboration, of course, with all the Integral team, it was to put a lot of effort in the development of an online system that automatically reacts to alerts from not only gravitational wave observatories, but also from neutrino observatories as well. And it performs a very quick analysis of the Integral data. So a bunch of scientists on duty, again, 24 hours over 7 days per week, are looking into that. Every time there is an alert, we get a phone call, we wake up, and of course, we are able to look quickly in what Integral has to offer for this event and eventually inform the worldwide community. So this was a big effort, but the system is fully deployed and is working now, and we can react in a matter of minutes. And it's worth saying that integral itself, the satellite can be repointed in the direction of this event within a few hours. The record so far was 3.7 hours from the reception of the alert from the community to the repoint of the satellite itself. So it's indeed an instrument that can repoint quickly the accessible directions of the sky. Now let me change the key observational capability. So we spoke about large field of view and omnidirectional viewing, but large field of view can also be explored indeed to look for longer times in specific direction of the sky. One interesting place, of course, is our own galaxy. You can see here, you can easily recognize an image of the Milky Way, and now you can see how integral sees our galaxy. So all these white dots are indeed sources in hard X-ray and gamma rays, and in yellow you can see how large is the IBIS field of view, where you can obtain at once an image of the sky 30 by 30 degrees. So it's clear that with such large field of view, we can not only detect bright impulsive events, but also other kind of sources. So I would like to start with really a very incredible source that went off in 2015. It was observed, of course, also by Integral. Actually, this was so bright that it was recognized at the beginning as a gamma ray burst. So we got the famous phone call while we were in a conference in Mykonos. And finally, indeed, it was not a gamma ray burst. It was a very bright black hole binary. It's called V404 Cygni, that was in quiescence for 26 years. And then it underwent this very bright outburst. Actually, it's very bright because this source is quite close to us, only 2.4 kiloparsec away. And you can see from the light curve on the right that it got very bright, 50 times brighter than the crab in X-ray. So you can compare the light curve, of course, with a lot of variability typical for this source. Integral spent quite some time looking at that, and the data set obtained is so rich that, of course, it will be exploited by the community for years. I think one point worth mentioning here is that this black hole was found to have a wobbling jet. This is a kind of peculiar property, and it could be looked into very high details. And this is thought to be due to the strong gravitational field of the black hole that is, of course, dragging the space-time with it. So while wobbling is, of course, bringing the jet with it. So you can see that the jet is changing direction over time. Another very interesting source, more recent, this one is a 2020 result. Integral is still full of surprises. In this case, the discovery was a strong X and gamma ray flare that was spatially and time coincident with a fast radio burst. So for those of you who are not familiar with fast radio bursts, let me just mention that these are objects showing short flares in radio from 1 to 10 milliseconds. They were of unknown origin. Now, theoretically, people were already expecting that these events could generate from magnetars. These are hypermagnetized neutron stars. So when you have some kind of reconfiguration of the magnetic field, weird things can occur. And the flare that was detected by Integral is a typical flare of a magnetar. So basically, as you can see from the bottom, the up plot, these coincidences confirm the long-sought connection between magnetars and fast radio bursts. So indeed, this was another key result from Integral and very recent, just a few months earlier this year. Now, there is another topic that I would like to deal with before going to the end in the next 15 minutes. This is actually my own field of research, so I'm particularly willing to show something about this. And now we focus on the fact that Integral is also the instrument allowing us or granting us access to what I call the millicrab fast transient universe. So the fact that the integral is staring at the sky for so long, several days in a row, allow us not only to detect these bright and transient events, but also fast and transient events at a much lower flux, so about 1,000 times lower than the crab, rather than 50 or 100 times higher than the crab. And in the millicrab level universe, we do find a lot of hidden pairs that so much as to tell us about, for example, the accretion physics. So let me show a few examples here. I start with the so-called supergiant fast X-ray transient. These are sources entirely discovered by integral. As you can see from the list of objects here, virtually all of them start with the IGR, meaning that they are discovered by integral. These are fast transients, so you can see on the top left the sequence of ISGRI image. Each of the images lasting 40 minutes. So you can see that in a few hours, the source appear and disappear from your detector. And since they show these sporadic outbursts of just few hours, having a large field of view with a great sensitivity is the key to discover these objects. Now, why they are so important? Because after 15 years of research, we know now that these objects are binary systems containing a neutron star coupled with an OB supergiant. In the next slide, I would just like to show you a comparison between, let's say, this kind of object that we knew before, even before integral, the so-called classical supergiant binaries. Again, if you have a neutron star around a supergiant, you expect that it is accreting wind for most of the time. So you have the wind of the star that is blown toward the neutron star. You have accretion, you have release of X-rays. You have a lot of variability, as you can see here in VELEX1, that is the prototype of this object. But the typical variability is around 10 to 50. And every time you look at them, the average luminosity, let's say over one day, is more or less constant. On the right, you see the light curve in X-rays of a supergiant fast X-ray transient. You can see that if it was a normal system, basically it should have had a luminosity above the dashed red line. Instead, this one is dramatically subluminous, and also it shows a variability that is not a factor of 10 to 50, but is a factor of 10 to 6. So what is incredible about this object is that it's hard to find an explanation because you have the same ingredients as the classical system, but they behave in a completely different way. So there are different hypotheses on the tables, but the solution is far from being found. One idea is that there could be a dichotomy in the winds of massive stars. So some of them could have a much more structured wind. And this will have actually important implication on many fields of astronomy and astrophysics, because you know that the wind of massive star is affecting the way in which you estimate the mass loss rate. That, of course, has also consequences on the galaxy evolution, the chemical enrichment, and so on. So it's a really important point to study. And then another possibility is that instead there is something peculiar with the neutron star. For example, a very high magnetic field, like in the case of the Earth and the Sun wind, where this magnetic field is blocking accretion and does not allow the release of X-rays. As in the case of the Earth, of course, it blocks the Sun, so likely there is no accretion of the Sun wind on the Earth. Or there could be even other peculiar accretion mechanism that we are trying to understand, but again, it's an open field and is very highly debated. Now, another key class of object is the one of accreting millisecond X-ray pulsars. These are also part of this, what I call the millicrab universe, because these objects are comprising a low mass star at this time, a star that is 0.1, for example, solar masses, and a neutron star that is accreting the material lost by the star through an accretion disk. Now, what is important about this object is that these objects are giga years old, and since the neutron star is accreting since so much time, all the angular momentum transferred by the accreting material onto the star is leading to spin period down to milliseconds. So the neutron star in this system is really spinning very fast. And these are, right for this property, key objects to access the physics of supranuclear density matter, so above 10 to 14 grams centimeters to minus 3. So these are really important laboratories because accessing the physics of the supranuclear density matter is very difficult to be done everywhere else. And there are different ways with these systems to access this kind of physics. There is also another important aspect that is an evolutionary aspect. So we know in our universe we have a millisecond, accreting millisecond X-ray pulsar, so pulsar spinning at millisecond in the X-ray domain, but we also have pulsar spinning at millisecond in radio, showing little to no X-rays at all. And it was expected in several decades that basically the accreting millisecond X-ray pulsar, as it is shown on the right, they are the progenitor of this isolated radio pulsar. So what happens is that they spin up to millisecond. At some point, the accretion stops. You have the radio pulsations turning on. This can completely evaporate the companion, so they are left with isolated radio pulsar. Now, on the first aspect, that is the discovery and the characterization of this accreting millisecond X-ray pulsar, again, integral has played a more and more important role in the past years because these objects are not constant emitters of X-rays. Those are transient, so they spend most of the time in quiescence, showing no X-ray, and from time to time they show an outburst, so emission of X-rays lasting 1 to few weeks. So either you have a large field of view or you cannot discover them. And as you can see from this list on the left, basically the amount of red sources, so those discovered by integral, is increasing over time because integral is being left as the only instrument not only to discover new sources, but also to discover new X-ray releasing events from already known sources. And of course, it is a very well-suited instrument to study other properties of this object, for example, thermonuclear bursts. So these are thermonuclear explosions that occur where you have material accumulating on the surface of the neutron star, and at some point is being emitted, so you have a fast flash of X-rays. You see this double peak in the ISGRI energy blend. It's a demonstration that during this thermonuclear burst, the whole atmosphere of the neutron star was actually lifted up and then fell back onto the star at the end of this event. And of course, integral can also provide a characterization in the spectrum in the timing domain, for example, measuring the pulse profile to the millisecond accuracy. That is very important to access, again, this physics of supranuclear density matter. There was a key result provided by integral in 2013 in this context, in the context of the evolutionary scenario, and it is the discovery of the first truly swinging pulsar, millisecond pulsar between the radio and the X-ray domain. So this was an object discovered by integral, and it was observed to switch, so to turn off in X-ray and turn on in radio on a time scale of weeks. So basically, it was really the missing link to finally prove this pulsar recycling scenario that I was telling before. So on time scale of weeks, you could really observe the X-ray pulsation turning off and the radio pulsation turning on. So again, demonstrating these cycles we have been mentioning before. Now, these are only a couple of examples. The millicrab universe is really rich of hidden pairs. It's a complete zoo, and we are far from having a full overview of all the possibilities. I just wanted to mention here very briefly two other interesting examples. The one on top is an X-ray transient source discovered by integral in 2014 that was later understood to be the disruption, to be caused by the disruption of an exoplanet by a white dwarf. So integral teaches us how to destroy an exoplanet and what happens when you do so. So a very, very singular, interesting event. And the one below, it's instead another result from 2018, where we saw for the first X and gamma ray light coming from this source is a symbiotic X-ray binary. So is a very old binary system comprising a red giant and a neutron star that actually we believe turned on for the first time. So it started a new part of its evolutionary path. Okay, these are only a couple of examples. Of course, there are many more results in integral. It's a long history, so it's difficult to be summarized in more details in 45 minutes. But I hope I did give you a good overview. So let me go to the conclusions. First of all, as you may have realized, the integral has just completed 18 years in space, the 17th of October 2020. So happy birthday to integral, and to me as well, because actually my birthday is also by chance October 17. So I always celebrate it with integral. We have to keep in mind that originally the instruments were designed to operate for 2 years. So we widely exceeded the lifetime of the mission, and it is because, of course, the design was very robust. I also hope I show and I convince you that after 18 years, integral not only has provided key results, but still provide breakthrough discoveries. The last one just earlier this year, a few months away. It also turned out to be a fundamental partner in the multi-messenger astrophysics. It brings with it unique observational capabilities that are not going to be overcome in the next decades because the replacement is not planned yet. And of course, it allows us a unique access to this milli-crab universe that we hope to continue in the years to come. Now, if you ask me, the spacecraft and the instruments are in very good health. Of course, they suffered some aging, as all of us, and they especially because they are operating in the harsh space environment, meaning the radiation, basically. But everything is going smoothly. There was some issue with the onboard fuel a few months ago, but there was a large effort by everybody in the teams to fix this, and this has completely been fixed. So we almost recovered the original efficiency of the mission, so nothing really to be worried about. And indeed, recently the operations of integral have been formally extended to the end of 2022. After that, we will have to evaluate again. So ESA is now looking to new creative ideas from the community in order to possibly plan the third decade of operations for integral. We could, in principle, continue up to 2029. At that moment, is already planned a controlled re-entry maneuver that is needed to avoid integral to fall into unwanted place on the Earth. But until then, of course, we still have several years to come. So stay tuned. And of course, with these very beautiful scientific capabilities, expect the unexpected, as we say. Thank you very much.
So, dear Enrico, I have to say a beautiful, wonderful talk. Thank you so much. I know it's not easy after 18 years of operation and 18 years of success, to find the breakthrough and to show that EC is a game changer mission. So I know there are much more results of integral, but I think you went directly to the point of what was really also unique and why integral is still unique. So to all the participants, you have now a two-way to ask questions. One is through the chat or just by raising your hand. Now we have already a first question, and it's from Alex. Let me see, there are so many questions now. There was one question is that, let me find it again. Well, I can't remember. It's, after 18 years of integral, how looks like a new mission, that can be compared to integral as a game changer mission.
Okay, so as I mentioned in the presentation, as of today, we still don't have on the timeline a confirmed replacement for integral. we have a number of missions in the X-rays coming along. For example, Theseus for gamma ray burst. We have Athena for the softer X-rays. But in the hard X-ray to gamma ray domain, at the best of my knowledge, there is nothing confirmed. Of course, this doesn't mean that people are not planning for it. For example, we have the AMEGO or the astrogam concept that have been put on the table to be the successor of integral, because they are looking indeed in the similar energy bands. But there is not yet, as far as I know, a slot confirmed eventually for this mission. So it means that since the development of the missions, either you do it in NASA, JAXA, or ESA, it's very long. It takes years. It means that at least, I would say, for another decade, it would be difficult to replace integral, to improve over these results. I think one important point, for example, it's of course the multi-wavelength domain. Integral allow us to be less blind that we would be without it, because it provides this omnidirectional view, and this cannot be provided on the short term by any other facility. We have Fermi, of course, but the two missions are largely complementary. So it's important to have both of them, and in some cases, it's actually very important to have a confirmation of the same results by more than one instrument, especially if you are close to the threshold of the detection limit. But again, in this energy band, we still have to look for a suitable opportunity. Of course, from now to 2029, it's difficult to imagine that something similar will appear. So we hope to keep integral alive. Another important point, of course, is that of the millicrab universe. We have several facilities counting on integral. For example, for the very important millisecond X-ray pulsar, we have a NASA experiment that is called NICER, that is basically designed to look at these objects. But if you don't have integral telling you where these objects are going off, then you don't know where to look at. So without integral, we will be blind in this sense.
Enrico, you have a lot of questions and 3 raised hands. I will first go through 2 more questions from the chat, and then through in the order I see the raised hand, we will go through this 3 raised hand. The first of one from Hugh Katzen, and he's a solar astronomer, and he would like to ask you if you can make a brief summary, let's say, or say something very brief about solar observations.
I don't know about this. I don't know if integral is, sorry, this is something I really cannot answer. I don't know if it ever looked, I think it will be quite difficult. I'm not sure we ever looked at the sun.
It's not really designed to observe the sun like XMM Newton.
No, of course not.
There are not so many sun. Integral has not been designed to observe the sun, no. Yeah.
No, of course not.
So now, Ilek El Melahat from the chat, he has a question. I will unmute him. Let's see.
You hear me?
Yeah.
Yeah. Thank you very much. So thanks, Enrico, for this great talk. And I had a question in your slide 27 about like the second scenario to explain the high level of variability you observe in superfast X-ray transient. So I feel like the second scenario is more likely because Rainer Heinisch and collaborators earlier on this year, they reported that there are like no systematic differences between like the stellar parameters between superfast X-ray transients and more classic supergiant X-ray binaries like Vela X1. So unless the neutron star can fragmentate the wind, I don't see why the clumping would be different. But if you go for the second scenario, then my question would be about the duration of the flares. Does it tell us something about the quantity of material which piled up on top of the neutron star magnetosphere between 2 flares, or is it going to be dominated by the outflows during the propeller phase?
Yeah. So okay. Of course, this is a very interesting question. So I want to answer in a very neutral way, although of course this topic is very dear to me. So for the dichotomy of the stellar winds, I agree with you. There are recent observations showing that this is unlikely to be the case. But if you want to take it from a neutral point of view, there are still people who believe this is not completely excluded, because performing observation, so measuring, let's say, the stellar wind parameters, either from isolated supergiant or from high mass X-ray binaries, is still affected by a lot of unknowns. So I would say that we are not yet at the point of giving firm conclusions, although it's true, as of today, it's difficult to find some strong convincing evidence in favor of this hypothesis. But in my opinion, it's not completely ruled out. For what concerns the second mechanism, so the first point here is that what you want to do is first to explain, sorry, I'm going back one slide, the reason why these sources are so much fainter on average compared to the classical system. We're speaking a factor of 1,000 or so. So the system that you see here is really focused to say, okay, how can we block accretion? Because we know the stellar wind is there, so something has to block the accretion to make this object fainter. And the only way we could think about is indeed either having a strong magnetic field or some physical effect that is blocking, that is impeding the material from entering the neutron star magnetosphere and go below. After that, so the next step, dealing with the flare duration and the repeatability of the flare, I think this is strongly related to, so if you consider the magnetic field case, it's strongly related to the clumpiness of the wind. So if you have many small clumps, so the point is that to allow accretion sporadically, you need to compress the magnetosphere. So you need to have a clump that is massive enough to cause this compression to enter the neutron star magnetosphere and then to be accreted and produce the flare. Now, as far as we know about this clump, if we take the measurements from the hydrodynamic simulation of supergiant stars, you do have sizes of the clump that will be comparable with the crossing time of the clump through the neutron star magnetosphere, so it could be explained. Considering the repeatability, this is a very difficult estimate, because the bright outburst like the one I'm showing here that goes off scale and touches the dashed line occurs, I don't know, a few times per year. So then if you want to make an estimate of the accumulation of material before this go off, I think is quite complex. But of course, you have a lot of free parameters also in the magnetic field. So depending on the average density of the wind, the size of the clump, the strength of the magnetic field, the strength of the, the rapidity of the pulse period, and so on, you can have plenty of ways to explain that. I think we have too many free parameters as of today. So we are not lacking the mechanism, we are lacking some more constraint to understand if those are feasible or not.
Okay, thank you very much.
Enrico, we have still two more raised hands and a lot of questions. Of course, I cannot go through all the questions. So if you can also give a little bit quicker answer would be very nice. So the next raised hand is Jeff Scardell, and I will unmute him. Yes, Jeff.
Yes, thank you very much. Congratulations on this wonderful mission and excellent talk. I'm particularly struck by how nicely this mission combines the time domain and energy spectral domains. Some missions focus on one or the other, but Integral has beautifully combined the two. I'm particularly interested in the millicrab universe that you talked about from the point of view of AGN variability. The notion of the big flares that we see and go off and chase sometimes are really just the high end of a spectrum of variability on very low levels. So can you comment at all about AGN variability?
Yeah, okay, yes, of course, AGNs are also a class of objects that are at reach for Integral. These are, let's say, relatively faint. So the object I I talked to you about, indeed, they go up to about 10 to 50 milligrams and so on. So you see here the conversion in flux. Many of the AGNs are quite faint. So I'm not sure, I mean, many of them have been, of course, observed by integral, also for variability study. I think one of the key observations of integral for AGN was to observe rather the obscured ones, those that are largely extinguished in soft X-rays, but they are actually shining in the hard X-ray domain. So there is a catalog of the obscured AGN by integral. I don't have at hand the number of sources that have been detected and which kind of variability scale you can observe. It's not really my field, so I will have to look into that. But indeed, that is another of the key results from integral. I did not have the time to report here. But again, for the obscured source, integral has provided a lot of results. So that is clearly, in the IGN context, I think the most critical result that integral has provided. Again, it's not my field, so there may be others that I do not fully know. But,
great, and just very quickly, did you get polarization results for V404 SIG?
Yeah, I did not report it because, again, let me speak from a neutral point of view. I think there was some measurement, but there is a debate around this measurement. I'm not aware if it has been solved or not, but yes, there is a paper with a polarization measurement. So let's say I reported the Sinus 6-1 polarization because it shows the capability of integral to do that. Again, there are in several topics, let's say, open debates. So I try to report what is firmly established. But yes, in this case, there is a polarization measurement, and there is a paper that you can look up on ADS with all the details. But sometimes when detections are debated by a lot of experts, it's also difficult to give a politically correct conclusion. So I'm not that expert to distinguish between these results. But there is a measurement, and of course, I'm sure that people are still looking into this data because those are it's a very, very rich data set.
Yes,
So
thank you very much.
One more question now also from Roger Bonnet. Roger, please.
Can you hear me?
Yes, hello.
Okay. I am very happy to be here listening to you. You have really described a mission which in 1993 I started to introduce in the ESA program. And at that time it was foreseen as a mission in collaboration with Russia. Of course, there has been a lot of activities involved with all the scientists in Europe in the program, especially in the data analysis. But this data, which you described so well, congratulations, would not have been possible without the people who really sweated hard to build the instruments. That was very difficult, very, very difficult. From people from Russia, from Italy, from France, from Germany, from Spain, and from Switzerland, where you are. I think I would like to insist on top of what you have said, that these people really deserve also congratulations for the fantastic success of this mission. Thank you.
Yeah, I fully share your feeling. I miss out reading the sentence that you can see now on the screen. I stressed here that, of course, this presentation is not the outcome of my own work. I contributed little to it, but is the outcome of many years of hard work, as you said, by a large community. And the exceptional work that has been done is now, I mean, it's undoubtful given that this mission is successfully and smoothly operating after 18 years. It's a lot of time considering that the instruments were designed initially for 2 years. So it means that they have been built really, really well. So of course, we have to thank a lot of people. Some of them left or changed the field, But still, of course, without all these people, and I think we are speaking about probably several hundred people, this would not have been possible. And as Maurizio anticipated, it has been very challenging to put together these slides, summarizing a few out of the many results that Integral has provided. So yeah, that was part of my hard work, as I can say.
Enrico,
yeah,
one last question, but it should be really quick answer from Peter Kretschmar. He's asking, you know, if there are still interesting detection hidden in the archival data. After 8 years, I mean, you have a huge archival data. Are there hidden pearls?
I think
quick answer, and then we will stop the seminar.
Okay, the super quick answer is definitely yes. And there are people indeed looking back at the archive every year, finding other sources, because there are several ways to analyze the data, let's say, and to look for them. The pity, of course, is that these discoveries are made after these sources are eventually turned off. So sometimes it's also difficult to follow up all these discoveries because to truly understand the nature of this object, you also need observations in other wavelengths, for example. So clearly, if you discover the event, the transient source, when it's already turned off, well, we just have to be lucky again for this object to turn on again. But every time there is a discovery, last few sources, I think just a few months ago, we include them in the catalog that is used for the near real-time processing. So we are sure that if this object turn on again in X-rays, we won't be missing its new outburst as soon as it happens.
So, Enrico, I think if I see the chat, we can really say congratulations. It has been wonderful talk, excellent presentation. And I would like to remind to all the participants that it has been, the online seminar has been recorded, and you can find it from tomorrow on the EC webpage. And I would like again to thanks to all the participants, and thank you, Enrico, once more for everything.
Thank you, Maurizio. And of course, thanks Integral, because it's his job to provide results. So I just showed what has been achieved thanks to this wonderful mission. So thanks everyone. And of course, you have my email address on the first slide. So if somebody is interested, please do not hesitate in dropping me an email. I will do my best to provide answers as quick as possible. Thank you, Maurizio. Thank you. Thank you, everyone.
And please stay tuned to the next online Game Changer seminar on November 12th. It's next Thursday on the dynamic sky in 3D based on Gaia given by Anthony Brown. Bye.